The purpose of this experiment is to determine the lasing threshold, that is the optical pump power, necessary to make a DPSS oscillate. The setup that we're using here is to have two DPSS's, one here and one here. The difference being between them, this one is an actual DPSS that has the KTP crystal and the little vanadate crystal attached to it, right there. And this is simply the pump diode from that same DPSS. Now they were identical at one point. We literally removed the DPSS from the front of this unit, leaving only the infrared diode. In this case, it's already powered up, and you'll notice approximately 33 milliwatts of infrared being emitted from this laser diode right here. Once again, a close-up of the actual setup. This is simply an infrared pump diode, puts out 808 nanometers. This is the complete DPSS setup, in which case the identical diode to this one is pumping a vanadate crystal, which has a KTP attached, allowing production of green radiation. The power meter can be inserted in this slot, in which case it intercepts the infrared beam, or in this slot, in which case it reads the green output. The experiment begins by determining the characteristics of the pump diode, which, as we said, are identical for both this diode alone and for this DPSS system. We first set the wavelength of the actual meter. You'll notice it's currently set for 633 nanometers. This diode operates at 808. So we'll first set the correct wavelength. .808 nanometers. Save that. And as with any reading, we'll zero the power meter. Now that everything's zeroed, I start increasing the current in increments of about 10 milliamps or so. Now I'm just going to vary it continuously from about 0 milliamps all the way up to its maximum of 275 milliamps. As I increase it, you'll notice that there's a power reading showing. This is primarily spontaneous output right now. In other words, it's acting like an infrared laser, an infrared LED at this point. When we hit the threshold current for this laser diode, you'll notice a dramatic increase in output power from the microwatt range to the milliwatt range. All of a sudden, we're getting milliwatts of output, indicating that the laser diode is actually operating as an actual laser at this point. And if I keep increasing the drive current at this point, the laser output becomes stronger and stronger until I hit its maximum value at 275 milliamps of about 38 milliwatts of power. Graphing this on a curve on, for example, Excel will allow us to determine the threshold and the slope. And it also allows us to determine the output power of this infrared laser diode for any given arbitrary current. I've now switched over the current source to drive this laser, which, as I said, is identical to this infrared laser, but now has the DPSS in front of it, which produces green radiation. I've set the power meter to 532 nanometers, and to show you what happens before I take readings, I'm going to put this green card in the way so you can see the green output of the laser. Once again, when I start increasing the drive current to that infrared diode, you see nothing evident. there's probably an infrared coming out, but it's spontaneous. At some point, the laser diode will start to produce laser output and drive the DPSS. But that doesn't mean that you actually get output from the DPSS at all. As a matter of fact, even though you have infrared going from that diode and hitting that DPSS and pumping it, you're still not overcoming the losses of the DPSS itself, which includes the mirrors on the DPSS laser, as well as the actual KTP inside the cavity and the actual attenuation due to the vanadate. So we need a lot more drive current to threshold this laser than we did this laser. We keep increasing and increasing, and at some point a little bit of green radiation should become evident on that green card. There we go, right there. At this point, the amount of infrared that I'm producing here from that laser diode is high enough that when it drives the DPSS, enough gain is produced within the vanadate to overcome all the losses within the cavity, and the laser oscillates. At this point, the laser has thresholded and it's producing green output at 532 nanometers, and as I increase the amount of drive current to that LED, to the infrared laser diode, you'll of course see an increase in the amount of green radiation coming out. Let's observe the output of the DPSS at 532 nanometers again, this time using the power meter. As usual, we zero the power meter, and then I will increase the drive current to the infrared laser diode that's pumping the DPSS very slowly. We don't observe any actual output at this point, and part of the reason is there's a filter on the front which blocks everything except for 532 nanometers. So we're not going to get any stray radiation from the pump diode in our readings. Now I'm up around the threshold point of the actual infrared laser diode. And you'll notice a very slight increase from the DPSS. We're now in the microwatt range. What's happening, of course, is that we're measuring spontaneous output from the DPSS itself. It is being pumped by the infrared laser diode. It is generating gain, but not enough gain to overcome all the losses. So we don't actually have a DPSS laser output yet, but we do get spontaneous output. As I continue increasing the drive current, that is, I'm increasing the amount of infrared that's pumping the DPSS, you'll notice a very slow increase in spontaneous output until all of a sudden you get a massive jump in the output power of this laser. At that point, the DPSS is actually operating. And we're starting to see that jump now. And there it is. If I observe the output, we see a green output, of course. And as I continue increasing the drive current to the maximum for that laser diode, the output in the green is also seen to increase. Here you can see the output from the green DPSS, and I'm intercepting it with a little card. Obviously you can't see the infrared output when we do that part of the experiment. You rely on the power meter for that. The laser diodes, both the bare laser diode and the one that's driving the DPSS laser, are both driven from this precision current source. The precision current source allows you to go from about 0 to 500 milliamps in any arbitrary number. One important feature of this current source is the ability to limit current to a value which will keep the laser diode from burning up. This is set using the limit feature of the actual precision current source itself. And in this case, it's set for 275 milliamps. When I turn on the current source, I can then vary the current all the way from 0 up to that maximum value of 275. At which point I hit the current limit and it simply won't let me go any higher. As I vary the current of the actual source, you'll notice that the output of the green appears and becomes brighter up until that maximum current. Interestingly enough, despite the fact our eyes cannot see the infrared output from the laser diode, the camera can, and it shows up as a faint purple glow, as you'll see. I have the laser diode itself, the bare laser diode, wired to the current supply, and as I increase the current, you'll begin to see a faint purple glow. There it is right there. The laser diode is now achieved threshold and is producing laser output. And as I continue to increase the current to the laser diode, the amount of infrared increases. Once again, you will never see this with your naked eye, but a camera will be able to see this. Oftentimes, a cell phone camera can see this as well.